Hello, everybody, and thank you for joining us for this session of Vertica Unify 2021. Our next breakout session is entitled Scalable Time Series Analysis and Forecasting. I'm Paige Roberts, Open Source Relations Manager at Vertica. I'll be your host for this webinar. Joining me is Vertica Product Manager for Machine Learning, Waqas Dillon. But before we begin, I encourage you to submit questions during the virtual session. You don't have to wait till the end. Just enter your question into the Q&A box on the right-hand side of the screen as it occurs to you. There will be a Q&A session at the end of the presentation. We'll answer as many questions as possible during that time. Any questions that we don't address, we'll do our best to answer offline. Alternatively, you can visit the Virtual Developer Lounge to ask additional questions and continue the conversation with our engineers and product experts after the session. And yes, before you ask, this virtual session is being recorded and it will be available to view on demand this week. We'll send you a notification as soon as it's ready. Now be sure to stick around to the very end of the presentation for the code you use to participate and gain points in our Analyze to Win competition to win prizes. Now let's get started. Over to you, Waqas.
Thank you, Paige. Hi, everyone. So before we go into time series analytics, I just wanted us to get a quick refresher of what is Vertica and specifically what is Vertica machine learning. As a lot of you might already know, Vertica supports the end-to-end machine learning pipeline. There's a ton of analytics functions that are already part of Vertica. And we actually have 5 major ways of doing machine learning or advanced analytics with Vertica. The first being SQL, that many of you already know and come to expect of data warehouse like Vertica. You can write SQL functions just as you do for joins. You can write SQL functions for machine learning, time series, geospatial analytics, and a lot of other analytics capabilities in the data warehouse. The second one is actually VerticaPy. So this is a Python API which enables you to write code in Python but push all the processing down to Vertica to be able to run those analytics at scale and at really fast speeds. The third method is user-defined functions, whereby you can write your own custom functions and bring them to Vertica. And this can be done in 4 languages. You can write them in Python, you can write them in R, you can write them in C++ or Java. 2 of the newer functions that we have added in the last 1.5 years include model import and export capabilities. First of them is actually TensorFlow, which enables you to bring any models that you have trained using Keras on top of TensorFlow or TensorFlow itself. And these models you can build in GPUs, in any other architecture. It can be cloud, on-prem. As long as it's stored in TensorFlow's native graph format, you can then bring that model into Vertica and you can run predictions in Vertica. Now, mind you don't have to build those models that are already supported by Vertica. Any algorithm that you don't already see in DB, you can still bring that in TensorFlow. So that means you can also bring in neural network models using this approach. Finally, PMML is a kind of language which is understood by a lot of machine learning tools. So let's say you have trained your models in Spark or Python or some other tool which supports PMML export. You can then export those models in PMML format, ingest them into Vertica, and then use them for model storage, model archiving, as well as prediction on all the data that you have in Vertica. So a really cool functionality there. Another piece of functionality here is the export part, where you can train machine learning models on really large data sets in Vertica. And let's say you want to do some prediction on the edge, you can export those models from Vertica to other devices as well. Within this, today we'll be focusing more on the initial 2 parts, the SQL API and the Python API. I'll be sharing some examples with you on the code snippets on how to write the code for that, for some of our time series functionality, in which we'll dive into in a little bit. So SQL, as I mentioned, might be already known to a lot of you. VerticaPy is something that enables you to write Python code, and it gets you the best of both worlds, essentially. Vertica is a columnar MPP platform. It provides you horizontal scaling, built-in highly scalable algorithms, open architecture, and is enterprise ready. Python, on the other end, brings its own benefits. It has a very high level of abstraction. It has object orientation, flexibility, and a very strong developer community. So with VerticaPy, we attempt to bring both of the best of both worlds together. So you get the syntax, you can write it in Jupyter Notebook or any other IDE of your choice that supports Python, and then push the processing down to Vertica, including model storage and all the other capabilities that you see. So moving on, Vertica time series is the topic that we'll be covering in more detail today. And within time series, let's just do a quick refresher of what a time series is. In practice, it's two variables. One is time, and the second is the value of the variable at a specific time. So each element of a time series consists of essentially the position in the time axis and the variable value. And the value at time t typically is not independent of previous values, and that's why we can use the previous values in the time series to predict or forecast values in the future. There's a lot of use cases of time series in the business world, in economics, in science, and stock prices, temperatures, sale revenue, number of unique visitors, the clicks on a page, essentially any type of data that you pick and you track it over time can be called a time series. So some other concepts around time series. In time series, we have trend, which is the overall long-term direction of a series. We can have a positive trend if it's moving higher. We can have a negative trend if it's moving lower. And sometimes we have no trend or a neutral trend, in which case it's remaining pretty much constant. The second concept is around seasonality. Again, it's the fixed known frequency, or in other words, you can call it the repeated behavior in the data which occurs at regular intervals. It's related to seasonal nature or human nature. The third one is cycles, which occur when series follows up and down pattern that's not seasonal. Cycles can be of varying length. Sometimes series will have very little random variation. At other times, they'll have a lot of unexplained variation. And in every real world time series data, there are always irregularities that can be related to real world occurrences and sometimes are unexplained as well. So moving on, within time series, there's a lot of use cases, but we have clubbed them into three major categories. The first one is anomaly detection. If you want to find outliers in data stream, which is pretty useful in a lot of, again, applications in failed sensors, surges in write requests, abnormal network request patterns. And then we have forecasting as the other major domain in time series analytics, where you want to predict future values of the time series. It's useful for predicting things like device failure, for example. If you're doing predictive maintenance for stock prices, what would they be in future? Demand for rides in the case of Uber or other ride-sharing companies. So forecasting itself can also be used for anomaly detection to ask questions like, does this incoming value deviate significantly from my prediction? How confident I am in that this is an outlier. And there are other applications around pattern matching. Today, we'll be focusing more on the forecasting applications of time series. So whenever we are doing a time series analysis, there's usually a certain process that is being followed. You do not necessarily do all the steps in this, but most of the analysis would cover these in some way or another. So usually what you do is you get a time series and you do some pre-processing on that. It would be very rare that you'll find a time series that wouldn't have any trend at all. But most of the algorithms that you'll feed the time series into would assume that it's already detrended. So that's a part that you'll have to do as part of your pre-processing. Then if the series is not normalized, you'll have to normalize that data. Then there are some transformations that you might do, logarithmic transformation or some others, and some other steps that you could possibly do within pre-processing. Then comes the feature extraction part. So as we discussed earlier, time series is a timestamp with a variable value, but sometimes what happens is that there are other variables along with the original variable of interest as well. So sometimes you can combine those variables and do an unsupervised dimensionality reduction. So you can still capture the value from those, but have just two variables to plot or predict or forecast. Then you could also aggregate some values. For example, you could include average value over the last month for sensor 1, sensor 2, and so on. In terms of applications, there are numerous that you could do after this. You could build a model, you could forecast, you could predict outliers. essentially a lot of use cases that you could solve with this. So moving on to Vertica. Vertica, as I mentioned, there's a lot of steps in time series, and Vertica has a wide range of descriptive time series forecasting algorithms. They can help you with data preparation, analysis of time series, and we have been putting in more and more effort towards the predictive or forecasting algorithms now, which would help you do more of the forecasting. So we'd, in the interest of time, spend most of our time on the forecasting part. But there's a ton of functions that if you go to vertica.com, you can find in our documentation. And a lot of our customers are actually already making use of these functions, from event-based to gap filling, time interval-based aggregations, and a lot more. So now comes the question. Time series is all cool. It has a lot of use cases. That time series data is pretty prevalent in business, especially in the structured data space. So why would you use Vertica to do time series analytics as compared to any other tool out there? Now, Vertica brings some pretty unique capabilities to the mix when it comes to time series. And I would say the first and foremost is that you have your data, mostly hot data, mission critical, business critical, already in Vertica. So if the data resides there, why take it out and take it to a different tool to do your analysis? You can analyze and predict the data in the data warehouse. It gives you really fast speed, and you can essentially distribute your computing over multiple nodes in a cluster. So you can do it with a much bigger data set than you'll be able to do it in a lot of other time series tools, many of which are either single node or they are limited by the amount of memory that is available in a certain machine. So analytics in place, first benefit. Second, distributed computing. The third is the breadth of functionality. So there's a lot of tools in the market. Each one of them specializes in a certain domain. But with Vertica, you get so many functions, as I mentioned, out of the box that let you do descriptive analytics and general time series analysis. And now we are adding that forecasting capabilities to that list. So there's essentially a whole long list of functions that you can use in Vertica, and you can do all of your analysis in that as well. So moving on, let's just get into some of these functions that we've been talking about in Vertica. What are they? And some of them are forecasting. As I mentioned, we'll be focusing on some of those. We have built something, some other functionalities in beta, and we continue to build more. But there's some functions that can help you, including the Dickey Fuller test, for example. Let's just discuss that one first. So let's say you have a data set. In this case, I'm showing a commodities data set, and you want to predict the price of different commodities in the future. So this data set that we have starts essentially from 1986, goes all the way to August 2020, and has some graphs, as you can see here, for gold, oil, the spread of interest rate, VIX, dollar to euro conversion rate, and the S&P 500 value. Now, if we want to, let's say, do any analysis on this, including autoregressive analysis or moving average analysis, we want to first make sure that all these time series, are they stationary in nature or not? So that's sort of the prereq for a lot of the functions that we'll apply. So that's where the Dickey Fuller test comes in handy. So as I mentioned, we have VerticaPy, which enables you to write some of these tests. So in VerticaPy, you can run a test pretty easily. There's a stats package where you can import AD Fuller. And then in this statement, we are actually using a for loop, and we are checking all of these different time series. In your analysis, you might be only interested in one, so you might only be working with gold or oil, or if you were interested in all, you could get a really nice table which would give you the p-values, critical values, and stationarity as well. Now, something you see pretty nicely here in the bottom line is the stationarity, where it tells you that gold and S&P 500 are not following stationarity. Similar is the case for the spread. Now, with this, we can have more tests applied on this data set to make sure that our hypothesis or the results of actually first test are what they say they are. So we do the Mann-Kendall test. Again, it's testing the same thing, testing the time series for stationarity. When we apply this, again, stats package is what we use on VerticaPy, and run it on gold and S&P 500 in this case, two variables that we were interested in. We see that the trend, again, the bottom row here, is increasing for both gold and S&P 500. So that kind of verifies our assumption. Now we have to do some data preparation and some other steps to make sure that the trend is removed, or in other words, you can call that detrending. Some other tests that you can do here are plotting the values, so autocorrelation and partial autocorrelation. If we plot those using VerticaPy again, we can clearly see the influence of the last two values on oil price, which kind of makes sense. When the curve slightly changes its direction, what's happening is that it will increase or decrease until reaching a new local maxima or minima. So only the recent values can help the prediction in case of our models, autoregressive, or other time series models that we apply here. We can also from here create a correlation matrix and see how the different variables are correlated to each other. That's again some functionality that's available. You can plot those correlations and a ton of other functionality that we could do. But we'll switch gears here and move on to the forecasting part. So the first algorithm I wanted to discuss today with you is something that we have implemented recently in Vertica, and that's the autoregressive model. Again, a quick refresher on what autoregressive models are. Mathematically, it's the estimation of a value y at time t based on past p values. So not to confuse this with the statistical p-value, this is the value p, which shows the number of periods. If we write an equation for that, yt is equal to alpha, and phi is the coefficient here, which is the parameter of the model. Alpha is the constant, and then you have at the end epsilon, which is the white noise error term. So essentially what autoregression means is self-regression. And if we look at the equation, one interesting thing is that an observation y at time t depends on y t minus 1, t minus 2, all the way to t minus p. It's not t minus 0 because p is actually what is denoting the lag order, and that's something you can tweak in your analysis to make sure that you reach the right analysis. Now, let's look into how you can actually do that and how some of these time series look like. So here's an illustration of an autoregressive model. In this case, it's a time series data set of daily minimum temperatures recorded between 1981 and 1990 in Melbourne, Australia. Now, looking at the data, you can see that there's a cyclical pattern of temperatures here. But an interesting thing is that the mean and standard deviation, they seem to be constant over time. So it's a stationary time series. It appears that it's a good candidate for an autoregressive forecasting model. The AIR model that we build on this, it would represent each data point as a linear combination of the p previous data points, where p is the lag order that we just discussed. It's also called the lag observations or simply lags of the model. So moving on, we can do some other interesting illustrations on this. Let's see how changing the value of lag, the value p here, would actually change the scatter plots. So for these three lags, there is each time a nice positive correlation between yt and yt minus h. So we can even notice that as the lag increases from the left to the right, from purple to red and then yellow, you can see that the correlation is actually weakening. So the oval shape of the scatter plot is wider with a lag of 4 than it is with a lag of 1, for example. So this is indicative of a weaker correlation between yt and yt minus 4. Again, this is part of the analysis. Some other illustrations that can help are the autoregressive model in the form of correlation plots and partial autocorrelation plots. So this is a quantitative measurement, and it's a tool to measure these correlations. Both of them are essentially, the difference is that the autocorrelation function for a lag h measures the direct and indirect influence of yt minus h on yt, but the partial correlation, autocorrelation, actually measures only the direct influence of yt minus h onto yt by getting rid of the influence of all the data points between t minus 1 and t minus h plus 1 inclusive. The partial autocorrelation function is particularly useful for building a stationary autoregressive model. Typically, a good lag p for the autoregressive p model is chosen such that lags h is greater than p. So partial autocorrelation of h is null. As a result, p should be chosen as the index of the last non-zero PAC coefficient. So autocorrelation, essentially, again, sort of summarizing it, is how value at time t correlates with value at time t minus k. And in this case, stationarity is, again, an assumption. So looking at temperatures, that's an example that we started with. So just continuing that, here we are actually working with the lag. So lag p equal to 3, p equal to 30, and p equal to 100. In each of these cases, the comparison prediction is being done over 7 days. The yellow line is the data, the blue is the prediction. And there's actually many ways to compute the parameters of an autoregressive model. There's OLS, Euler-Walker, Berg's method. In this specific case, we are using a customized distributed linear regression implementation, which is based off of the algorithm already available in the Vertica toolbox. So just looking at these plots of temperature over 7 days with different lag values, now we switch instead from the last 7 days to the last 500 days. And you can see how the plot changes from previous slide to this. You see a lot more variation in the data itself, but the prediction is again a pretty nice smooth line. So if you want to implement this or use this in Vertica using the SQL API, there's a pretty easy and simple script for that. So you can train the model, select autoregression, give it a model name. You can tell it the name of the input table or any other input relation, views, timetables. You have to tell it the name of the column where the timestamps are stored. So here we are calling it the time series column, and the timestamp column using parameters. In this case, we are setting p equal to 3. Again, this is a parameter you can tweak and work with. In this case, any missing values that it finds, we're telling to interpolate those with linear interpolation. We're not applying any regularization. Lambda is 1, and compute sum of squared errors is set to false. So that's it. This is what you'll use to train your autoregression model, and it would be saved by the name model name. In this case, you could essentially give it some nice name with which you could remember it. So once you've done that, the model is stored in Vertica. Now, this is where it differs from other compute engines where you have to create a model and then you have to serialize that model and maybe later on deserialize that and run for prediction. With Vertica, compute engine and storage, they're together. You write the SQL statement, the model gets stored. The next time you need that model to make a prediction, you'll use the below statement, select predict autoregressor, time series column using parameters, and here you'll give it the model name. Again, hoping that you gave it a better model name than I did, and you can recall that. So you write here the model name, you give it a start value. Here we are giving it 3. A number of predictions that you want to be done, 10 in our case of this example, and we also want this time series to be this output to be sorted. So we are sorting it by ordering it by timestamp column from input relation. That's the relation from where we'd actually be doing that. So that's pretty simple syntax for autoregression. So that brings us to the end of autoregressor. Let's move on to moving average models. So a lot of the graphs and the concepts are pretty much similar. The assumption of that stationarity is also the same. Let's just quickly look at the equation for moving average models. So the mathematical definition, it differs slightly, and that's where the whole point is, where these algorithms are actually brought together most of the time to use ARMA models or ANIMA or their further variations, because both of them have their own unique ability. So in terms of mathematical definition, MA is the estimation of a value y at time t based on the past q errors. So instead of the past values, we are looking at the past Q errors. Equation is yt is alpha, and then you have theta as the coefficients, which are the parameters of the model, and epsilon is the white noise error term. So one question that arises here is that how many past Q errors need to be taken into account for a certain analysis. The order of the equation is also something that's important, and we could actually figure that out using this next graph illustration. So it's pretty much similar. We have used the VerticaPy function plot ACF PACF. It would create both plots for you, the autocorrelation plot and the partial autocorrelation. In the case of in this example script, we've just told it to do that from commodities, column name, timestamp, and then instead of P, we can give a Q value because we want it on moving average. So you get your nice autocorrelation plot. You can look at the correlation plot, and that can help you determine how many past moving averages, what should be the right number of, or the right size of the moving average window that you should take to have a good forecast. In terms of the SQL API, it looks pretty much similar. Again, it's different in how it performs, but essentially you do a select statement, moving average, instead of the autoregressive model here. Similarly, you give it a model name, you tell it the name of an input relation, you tell it the name of the time series column and the timestamp column. In this case, instead of P, we are defining Q in our parameters. Similarly, linear interpolation, no regularization, and a lambda value of 1. You do this, the model gets stored by the name model name. Next time you need a prediction on a new data set, you do a select predict MA, tell it the name of the time series column on which it needs to make the prediction, tell it the name of the model that it needs to use to make that prediction. For this example, we're again making 10 predictions. You can make 20 or any other number that you require based on your use case. You just have to point it to the input relation, which is, and a relation is essentially just a table, a view, or a time table. So that's it. That's as easy as that. You can analyze your time series and forecast using these two models that we have recently built as part of Vertica. Now, the direction here onwards, as I mentioned already, is obviously to build ARMA next, and then ARIMA with the integrated component. But before we go there, what we have done is we have actually already built these time series model, and eventually SARIMAX is going to be the objective of this specific effort. There would be other models as well, but we have built a beta of SARIMAX already. So let's say you have a use case where you want to know how this would perform. You could actually use that beta today in VerticaPy and test it out. The only difference is why are we building this, or what beta lacks is only the part that, as I mentioned earlier, VerticaPy is a client-side library, and it pushes most of the computation down to Vertica for parallelization, for speed, and all the benefits that we earlier discussed. So initially, we did the implementation on the client side. There is some computation that we are slowly moving more and more towards the server side. In this case, so AR and MA are the first part of that, and the plan is to now build the remaining part as well. But SARIMAX, as I mentioned, that's already available in VerticaPy. It might not provide you the bestest possible speed that you might be used to with Vertica, but if it's a pretty good tool if you want to do a quick concept test and run it. Script, just have a quick look at that. It's again verticapy.learn.tsa. You can import SARIMAX from there, and SARIMAX means you can actually just do the ARMA component or ARIMA component or the seasonal by providing the right value. So here we're providing it the P value, the D, the Q, and by that we actually create a model for SARIMAX. Here you would see in the script, it's pretty similar to what you saw in the SQL script. You have to mention Amazon clean. That's the relationship from which we are actually taking this. Y is the number and TS is the date. So those three things that we saw in the SQL script, they are pretty similar here. Once you do that, you get the output on the right, which is details of the model that has been built. It will tell you the name of the coefficients, the intercept, and the arguments. and some additional information just to make sure that you applied it on the right table and you had the right columns identified for timestamp and the variable. Now, after you do this, you can look at the model. And for that, there's this pretty simple command that you'll use, model.regression report. So this is actually also helping you evaluate the model. So it gives you the explained variance through this model, max error, median absolute error, and a lot of other critical figures that you might want to look at. Now, if you wanted to plot this, VerticaPy comes with a lot of plotting capabilities, including dynamic and one-step ahead forecast. And they're actually pretty easy to use. Model.plot Amazon, number of leads 150 in this case, and we set dynamic to true. So you get this pretty cool graphic on the right. Now, VerticaPy has a ton of other capabilities. A lot of them are based on top of Vertica SQL. So essentially the same capabilities, but what we've done is that we have optimized a lot of them, just like in graphics, we have optimized them to be used on larger data sets. So that's one benefit that you get. The second is that it's actually pushing a lot of that computation. And as I mentioned, in the case of time series, we're working on pushing more and more towards the server. So you get the interface that you like in terms of Python, but you also get the performance that you like out of Vertica. So stay tuned for more on that. So in terms of roadmap, specific to time series, there's a lot of functions that, as I mentioned, we continue to build. AR and MA are expected to be part of the upcoming release. But in next releases, we'll be working on ARIMA, seasonal autoregressive model. Essentially, you also already saw the beta. Output would be similar. Performance would hopefully be a lot better. Then there's other models like Hold Winters, Gosh, Facebook's Profit, and others. So this is a continued effort from our side because a lot of our customers have this time series data. As I mentioned in earlier, there's a lot of benefit that they see to do that in Vertica. And that's why we'd continue on our journey to incorporate these algorithms as part of Vertica and publish them for our users to help them get more value out of their data. So with this, over to you, Paige.
Thanks, Vikas. If you want to learn more after this conference is over, remember that our Vertica Academy is always available for free on-demand training and certification. Now we're ready for Q&A. All right. Looks like we had a couple of questions came in. Let's see. The number one most voted for is, my team already uses R for time series forecasting. What would be the biggest incentive for them to instead do their time series predictions in Vertica?
Yeah, that's a good one. So essentially, all of the algorithms that you see in Vertica, especially for machine learning, you find those algorithms having been implemented in other tools like R and Python, and they've been around. Most of them have been around since the 1950s or 60s. So it's not really the algorithm that we're just innovating on or something super cool that we're bringing in terms of the algorithm itself. It's the same algorithms. If you're using it in R or some other tool, it would be the same thing. So that's where the similarity ends, though. The difference is that for a lot of these tools, let's, as you mentioned, the case of R. So R is a single node and usually memory dependent tool. What that means is that you can only do time series on the amount of data that can fit in the memory, and not just fit in the memory on which you can actually apply some of these computations. So you're seriously limited, especially for a lot of the big data applications that Vertica handles. Many of our customers were actually constrained by the data or amount of data they could handle in R. So there's multiple other things. R is not a data store. It's not a data warehouse. It's just a compute tool. So once you've built a model, you have to think about serialization and deserialization. Whereas in Vertica, there's no such thing like that. You build a model, it gets stored in Vertica. Next time you need to make prediction out of it, you just take it out of the disk storage and then just use it. So ton of benefits, but if I had to just pick one, I would say scalability, and scalability to the extent of data that you can store in the data warehouse, you can apply models on that, you can train and predict. I think that would be by far the biggest benefit. But all the model management capabilities, I would say that is the secondary big benefit that would probably the scalability would bring you to Vertica, and the model management capabilities is what will help you stick with it and get really more value out of it.
It's really easy to deploy that way too, at scale.
Yeah.
Okay, you showed two graphs, correlation and an autocorrelation graph side by side on one of your slides. Which tool did you use to make them?
Oh, the graph specifically. So the analysis, as I mentioned, you can do a lot of correlation and autocorrelation, including the AI algorithm that we now have. With those, you can do the computation, but the graphing part, if that's your question, then we use VerticaPy for that. As I mentioned in the beginning, we have a SQL API, we have a Python API for Vertica machine learning. So there's a lot of benefits that the Python API actually brings to the table. One is it's a client-side application, and it gives you a familiar Jupyter Notebook or other IDE option that you might already be familiar with. The other big benefit, especially for graphing capabilities, is that it has a ton of charts. Now, why would I just refer to the question that you asked earlier about R? So same thing applies with Python. Let's say you put a Python instance, a client machine, and you connect to Vertica, and then you can build some graphs there. It's pretty easy. Do Matplotlib or any other graphing library. The problem there is that Python is not optimized for scale. So let's say you ask it to build an autocorrelation plot on a really large data set of 1 billion plus rows. It would attempt that. It would probably run out of memory or some other problem with the database. If it's just trying to access it, there might be connection problems. Whereas with VerticaPy, we've already optimized it for one, having the syntax as close to Python as possible. I'd say it's pretty much similar. The second part is around optimizing the amount of data that's actually taken from the system. So what it's doing is it's a client program. It's connected to Vertica data warehouse. So it might be 10 node, 50 node, whatever the cluster size is, and then it pushes the processing to Vertica. But once that autocorrelation has been calculated, the client needs to be able to see that in a graph format, and that's what VerticaPy helps you do. There's a if you go to vertica.com/python, there's a ton of charting capabilities that you would see there, from static graphs to dynamic, and we keep on adding to that functionality. So these, in short, these graphs were built using VerticaPy. You don't need any extra traditional BI tool or any other tool to do this stuff. It's an open source library you can use.
Okay. One of the other questions was currently Vertica supports TF1. Any plans to support TF2? I don't even know what that is.
Yeah, if you could elaborate a little
TensorFlow.
bit on that.
Okay.
Okay. Yeah. So that's a good question. I would say right at the spot where we were actually upgrading that. So the good news is we have started supporting TF2 as of the upcoming release. Again, all the usual disclaimers apply. It's not a promise for delivery, but from our side, it's I would say pretty much done with QA. Dev is done. QA is almost done as well. So you should expect it
So
in the upcoming release.
Possibly in the next release. We'll see.
Yeah, possibly.
Possibly. No promises. Yeah. All right. Let's see. Arima, would you support seasonality for time series algorithms, especially for the ARIMA?
Oh, yeah. So for Arima, right now, what we have discussed again for others who might be wondering about the question. So there's two features in SQL API that we are supporting as of upcoming release. One is AR, the autoregressive part. The other is MA, moving average part. But as I mentioned in the beginning of the call, that the two things that it doesn't take care of, these two models, is that once you are inputting any data set into these, you have to make sure that there's no trend in your series and there's no seasonality. Both of these need to be taken out. But let's say you already have that. So one is you can use Vertica's lag functions and some other pretty cool data prep functions to take the seasonality and the trend out. But what you can do, and that's the plan for us, is that we will support Arima. So Arima is the I part is actually what takes care of the trend in the data set. Now the plan is actually to support SARIMA. So the seasonal
We're running out
Arima.
of time, so.
Oh, okay.
Sorry.
Yeah, so seasonal Arima is on the roadmap. That's where we're moving to, and you should see that soon as part of the offering.
Awesome. Thank you. We got some nice compliments on the presentation as well. That's all the time we have, though. We are completely out of time. So don't forget to type in your session code into the Analyze to Win section on the navigation panel, and then choose this session and enter the code for this session, which is Dachshund. And that concludes this breakout session. Have a great day, and we hope you enjoy Vertica Unify.